voice is audible now?
Yes, sir.
Okay. So last time we have discussed up to the reactions of the monosaccharides. Okay. So in that we have discussed the actions of the acids, like say if the monosaccharides are treated with the concentrated acid, then what products we got it, like say the furfuryl or the hydroxymethyl furfuryl. If the monosaccharide is either the pentoses or the hexoses, then we also discuss it when the monosaccharides are kept in the alkaline medium, then the enolization or the tautomerization reactions, then oxidation, the effect of oxidizing agents, reducing agents. So all that we have discussed it. And today we'll be starting with the derivatives of the monosaccharides. Okay. So in this, we'll be discussing only the important derivatives. So here, many chemicals, they may react with the groups that are attached to the carbon atoms of the monosaccharides. Okay, so the groups we know it is the hydroxyl groups. Okay, so these hydroxyl groups, it may react with the methyl group, it may react with the acetyl group, it may react with the amino groups. So many chemicals or the compounds, they can react with these hydroxyl groups to form a derivative. Okay, so since that product is formed by the reaction of some groups with the monosaccharides, they will be the derivatives of the monosaccharides. Okay, first is the methylation at the anomeric carbon, that is addition of a methyl group to the carbonyl carbon of the monosaccharides. Okay, so aldohydrogenase, it readily reacts with alcohol in presence of the mineral acids to form anomeric alpha and the beta glycosides. So here, what happens is that if you take the glucose, okay, so glucose, if it is allowed to react with the methanol we know that it is an alcohol. So if it is allowed to react with the methanol in presence of the acid, then this methyl group is attached to the OH group or attached to the carbonyl carbon, that is the carbon number 1. So we know that the hydroxyl group attached to the carbon number 1, it may be in the alpha configuration or it may be in the beta configuration. That they are the anomers that we have already seen it. So if the OH group is above the plane of the ring, we call it as the beta. If it is below the plane of the ring, we call it as the alpha. So two forms of the alpha D-glucose, two forms of the D-glucose will be formed, that is the alpha D-glucose and the beta D-glucose. So when this methyl group is attached to this group, then either that methyl group will be in the beta configuration or it will be in the alpha configuration. Okay, so that will form the anomeric alpha and the beta glycosides. The glycosides are asymmetric. So now, what is glycosides? Okay, so glycosides, these are the asymmetric mixed acetals formed by the reaction of the aldehydic carbon atom of the intramolecular hemiacetal or the pyranose from the aldohydroses. So we have already seen that the hemiacetal form of the glucose. Okay, so that the carbon number 1 of the glucose or the aldehydic functional group of the glucose, when it reacts with the hydroxyl group attached to the carbon number 5, that we call it as the hemiacetal. Okay, so that forms a ring structure. Now, if this reacts with another alcoholic group, okay, then that derivative it is formed. Okay, so the covalent bond that is linking that the additional or the methyl group to the carbonyl carbon, it is called as a glycosidic linkage. Okay, so and this product we call it as the glycoside. So glycosides, these are the asymmetric mixed acetals formed by the reaction of the aldehydic carbon atom of the intramolecular hemiacetal or the pyranose form of the aldohydrose with a second alcoholic hydroxyl group furnished by the alcohol. Okay, the glycosidyl linkage is also formed by the reaction of the monosaccharides to form the disaccharides. So here, if you see this product, okay, that can you see this one, that the cursor that is moving?
Yes, sir.
So this is from this CH3O. Okay, it is coming from the methanol. Okay, so methanol, it reacts with the OH group attached to this anomeric carbon, that is the carbon number 1. Okay, so what happened, that the OH group and this hydrogen, one hydrogen from here and the OH group from the methanol, it has been removed as water, and this methyl group is attached to this oxygen. Okay, now this bond, it is called as the glycosidic bond. Okay, so that this methyl group is linked to the carbon by a bond which is called as the glycosidic bond. Similarly, so this is below the plane of the ring, this configuration of this methyl group is below the plane of the ring, so this will be the alpha. Here the configuration of the methyl group is above the plane of the ring, so it will be n beta. So beta and alpha will be formed. Okay, these are the two products. So here the reaction is between the OH group of an alcohol, then OH group attached to the anomeric carbon, that is the carbon number 1. Okay, so reaction is between the alcohol and the alcohol. So similarly, if you see that two monosaccharide units, in the monosaccharides also there are many hydroxyl groups. So here if you see it, it is attached to carbon number 2, 3, 4, then 5, 6. Okay, so many hydroxyl groups are attached to the different carbons in the monosaccharides. Okay, so this OH group again, it is the alcoholic group. So this alcoholic group of the monosaccharides, it can also react with the OH group attached to the anomeric carbon. Similar here, it is the alcohol we have taken it, but instead of alcohol, it can be other monosaccharides also. So the OH group of the other monosaccharides can also be linked to the anomeric carbon. So similarly, this will be through an glycosidic linkage. The name of the bond will be glycosidic linkage. Okay, so like that, one monosaccharide can be linked to the another monosaccharide through the glycosidic linkage. This will form a disaccharide. So if another monosaccharide is linked in that fashion, then three monosaccharides has been linked together, that will be a trisaccharide. So like this, the many monosaccharides, they also can be linked together by the glycosidic linkages to form the polymers. Okay, that is one. Second, that OSL derivatives, that is the acyl groups, can also be linked to the hydroxyl groups of the monosaccharides. The free hydroxyl groups of the monosaccharides and polysaccharides can be acetylated. That means the acetyl group can be added. So if it is a monosaccharide, then this will yield OSL derivatives. Okay, then because acyl group is linked to the oxygen, so it is called as the OSL derivatives. Say for example, treatment of the alpha D glucose with excess acetic anhydride groups yield penta or acyl alpha D glucose. Okay, so what happened is that here we have taken the methyl group, but instead of the methyl group, if you have taken the acetic acid, okay, then this acetyl group will be linked to this OH group. So it will be the link to the OH group attached to carbon number 2, 3, 4, and so on. Okay, so since there are 5 OH group, okay, that is 1, 2, 3, 4, 5. That is OH group attached to carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 6. For carbon number 5, the OH group is involved in the formation of the chemical bond with the anomeric carbon, that is carbon number 1. So it is not free. The hydroxyl group is not free. So there are only 5 OH group which are free in the alpha D glucose. So that means the 5 acetyl groups can be linked to this. So penta or acyl derivatives will be formed. Similarly, if you take the methyl group, like the methanol, so in the earlier one, what happens is that when we do the reaction in a mild condition, then only the anomeric carbon will be reacted. That is, ethanol in presence of the acid to yield methyl glycosides, okay, which are the acetals. The remaining hydroxyl group is the monosaccharides require much more drastic conditions for the methylation. So if the methyl group is added to the OH group attached to carbon number 2 or carbon number 3 or carbon number 4 or carbon number 6, then it requires some drastic conditions. What is the drastic condition? The drastic conditions such as treatment with the dimethyl sulfate or the methyl halide. So we have to use some strong reagents to methylate the hydroxyl group attached to the other carbon atoms, that is carbon number 2, 3, 4, and the carbon number 6. Okay, then similar to the acylation or methylation, the phosphoric acid, it can also be linked to the hydroxyl groups of the monosaccharides. Okay, so whatever linkage it will be, when we know that when the reaction is between an alcohol and acid, that linkage we call it as an ester. Okay, so since here the phosphoric acid, this is an acid group, it is going to be linked to an alcohol group, so it will be an ester. Okay, you must be all of you must be knowing it, what is ester, what is ether, okay, and all that. So that see that. Okay, so phosphoric acid esters or the monosaccharides are found in all the cells in which they serve as an important intermediates in the carbohydrate metabolism. So when we discuss the metabolism, you will find that the intermediates of the carbohydrate metabolism, like the glycolysis. So that intermediates are phosphorylated. So there are some advantages for the phosphorylation of the intermediates that we'll discuss it when we discuss the metabolism. So like that, the monosaccharides, it may have the phosphoric acids attached to the OH group to one of the carbon atom. Okay, so here we saw that the phosphate group is attached, the phosphoric acid group is attached to the carbon number 1. So here it will be glucose 1 phosphoric acid, or simply the phosphoric acid at the physiological pH, they will occur in the ionized form. Okay, this will not occur since it is the acidic group, and at the physiological pH, their pK value will be much lower. Their pK value for the acids will be lower than the physiological pH. So at the physiological pH, these groups will be in the ionized state. So what will happen here? This phosphoric acid form will not be present, but it will be in the ionized form. So we call it as a phosphate. So it will be alpha D glucose 1 phosphate will be the structure here. Okay. So instead of the carbon number 1, the OH group attached to carbon number 1, this phosphate group can also be attached to the OH group attached to the carbon number 6. So here it is. Here the phosphate group is attached to the OH group attached to carbon number 6. So this is alpha D glucose 6 phosphate or the phosphoric acid. Okay. So simply, since we are giving the structure in this one, so we are just showing the acid form, but at physiological point, at the physiological pH, all these molecules will be ionized, all these acid groups will be ionized, so they will be calling as a phosphate. Okay? Glucose 6 phosphate. Okay, next is the deoxy sugars. So deoxy, the name suggests that deoxy means lacking a oxygen. A oxygen is lacking from these sugars. Okay, so the most abundant deoxy sugar found in nature is 2-deoxy D-ribose. So here it says that it is the ribose sugar in which the oxygen attached to carbon number 2 is missing. That is the 2-deoxy, that indicates means it is the carbon number 2 where the oxygen is missing. The sugar component of the deoxyribonucleic acids, that is the DNA. So in the DNA, we find that the pentose sugar, it is the deoxyribose. Then another one is the L-rhamnose, which is the deoxy-L-mannose, and the L-fructose, that is the deoxy-L-galactose, are the important components of some bacterial cells. Okay, so these are the important deoxy sugars that are found in the nature. So here, if you see the first one, that is the 2-deoxyribose. So here, that oxygen, it should be the second carbon. If you see it, it should be CH2O. Okay, CH2OH. So one oxygen is missing here. Okay, it should be CH2O, or you call it here, it should be same like this. Okay, CH on one side, OH on the other side. So here oxygen is missing, so only 2 hydrogens are present. So it is CH2. Oxygen is missing, so it is deoxy. Same thing here. If it is the one oxygen is missing at the carbon number 6 here. Okay, so if you see the whole, if oxygen is present here, that will be the structure of the galactose. Same thing, this will be the structure of the mannose if the oxygen is present here. So in all the cases, one oxygen attached to one of the carbon is missing. Since oxygen is missing, they are called as the deoxy sugars. Okay, next is the amino sugars. That means that amino group is present. Amino sugars means amino group is present in these sugars. So how it is present? They are present by attaching a amino group in place of the hydroxyl group. That means one hydroxyl group is replaced by an amino group. So when one or more hydroxyl groups of the monosaccharides are replaced by some amino groups, the products forms are called as the amino sugars. Okay, because it presents the amino group, because of that they are called as the amino sugars. The two sugars of the wide distribution are D-glucosamine and D-galactosamine. So D-glucosamine and D-galactosamine are two important monosaccharides, or the amino sugars that are present in the nature, in which the hydroxyl group at the carbon number 2 is replaced by an amino group. So what happened here is that the OH group attached to the carbon number 2 is replaced by an amino group. The glucosamine occurs in many polysaccharides of the vertebrate tissues and is also the major component of the chitin. That is a structural polysaccharide found in the exoskeletons of the insects and the crustaceans. So if you see here that this here in the carbon number 2 amino group is the NH2 group is present in place of the OH group. So that means that OH group has been replaced by this amino group. Okay, if it is OH group, it should be, well, what it should be the glucose. Now since the OH group attached to carbon number 2 is replaced, so it will be called as the glucosamine. Okay, it will be the glucosamine. Now if you see here, then if this instead of the NH2 group, if it is OH group, this should be a galactose. Okay, so since it is removed, it is replaced by the OH group at the carbon number 2 is replaced by the amine group, this will be an galactosamine. Okay, so these are the two most abundant amino sugars that are found in the nature. D-galactosamine is a component of the glycolipids. Okay, so glycolipids we have already come across when we discussed the biological membrane. So in the biological membrane, some lipids will be there, which are with the carbohydrates that are the glycolipids. And of the major polysaccharides of the cartilage, okay, the chondroitin sulfate. So they are found in the glycolipids and the cartilages, chondroitin sulfate, etc. We'll come to this later on. Then the amino groups of the amino sugars are sometimes acetylated. So this amino group, the acetyl group may be attached to these amino groups. Okay, for example, is that N-acetyl D-glucosamine. Okay. Here the N-acetyl muramic acid. Okay, so then N-acetyl glucosamine, then with some other groups, they form the different products. One example, it is N-acetyl muramic acid is a major building block of the polysaccharide backbone of the bacterial cell walls. Okay. It consists of the 6-member amino sugar. So here you see it, just see this portion, then this the glucose. Okay, we have the glucosamine. Then to the amino group, that's acetyl group is linked. So what it becomes is it becomes the N-acetyl glucosamine. Okay, just forget about the lactic acid part, the lactate portion, just for the time being, you forget it. That is the portion which is shown in the red color. Okay, so if you don't consider this, and if you see here only, okay, for time being, let's forget the acetyl group also. So you have the glucosamine here. To the glucosamine, now one acetyl group is linked to the amine group attached to carbon number 2, so it becomes the N-acetyl glucosamine. To this N-acetyl glucosamine, then another lactic acid is linked to the carbon number 3. That is through the OH group attached to carbon number 3. Okay, then whole this structure is called as the N-acetyl uramic acid. So N-acetyl uramic acid, it is just the composition of the glucosamine, then acetyl group and lactic acid. All these together, it forms the acetyl uramic acid. Okay, which is which is present in the polysaccharide, that the backbone of the bacterial cell walls. Okay. Then next one is the N-acetyl uramic acid. Okay. This component. So let's see what is this. N-acetyl uramic acid is derived from the D-mannose amine. Okay, so the parent compound, it is the mannose with the amino group, so it will be mannose amine. And pyruvic acid. Okay, it is an important building block in the polysaccharide chains found in the glycoproteins and the glycolipids of the cell cords of animal tissues. So N-acetyl derivatives of the uramic acid are generally called as the sialic acids. So let's see here. What do we have? If you don't consider this one, this will be the mannose. Then since it is the amino group is attached to the carbon number 2, it becomes the mannose amine. Okay, it becomes the mannose amine. Now to this amino group, okay, amino group attached to the carbon number 3, this group is attached. Okay, so this group is the, what is this? It is the acetyl group. Okay, acetyl group is there. Then finally to the carbon number 1, that pyruvic acid is added. Okay, so this product, it is N-acetyl uramic acid. It is also called as the sialic acid. Okay, so these are the very important that amino sugars that are present in the biological system. Okay, this is all about the monosaccharides, that what we have to discuss about the monosaccharides. Okay, next let's start with the oligosaccharides. So oligosaccharides, earlier in the previous class we have already discussed that if a carbohydrate contains 2 to 10, okay, if the number of monosaccharide units present is starting from 2 up to 10, then we classify these carbohydrates as the oligosaccharides. Okay. So the word oligo, it comes from the Greek, which means few. That means it contains few number of the monosaccharide units linked together by the glycosidic linkages. Okay. So since these oligosaccharides, it contains 2 to 10 molecules of monosaccharides, if they are hydrolyzed, then depending on how many monosaccharide units are present, that will be liberated. If the oligosaccharides contain the 2 monosaccharide units, then on hydrolysis, this will produce 2 monosaccharides. If that contains 10, then on hydrolysis, that will produce 10 monosaccharide units. Now, based on the number of monosaccharide units present, they are further classified as disaccharides, trisaccharides, tetrasaccharides, pentasaccharides, etc., respectively containing 2, 3, 4, or the 5 monosaccharide units. So based on that how many monosaccharide units are present in the oligosaccharides, they are further classified into disaccharide, trisaccharide, tetrasaccharide, pentasaccharide, hexasaccharide, heptasaccharides, octasaccharides, nanosaccharides, all that. Okay, so it will be called as per the number of the monosaccharide units present in that particular oligosaccharide. Okay, let's take some of the important examples of the oligosaccharides. First, we start with the disaccharides. Okay. The general formula for this is the CnH2ON-1. This is the general formula for the disaccharides. Okay, on hydrolysis, they will produce two molecules of the same or the different monosaccharide unit. So since it's a disaccharide, they are made up of the two monosaccharide units. So on hydrochloric acid, they will be producing two monosaccharide units. Example is the maltose, which is a disaccharide form by linking one glucose to the another glucose. Means two glucose units are linked together by a glycosidic linkage to form a molecule. So that is the name is the maltose. Okay. Now, see, this is the structure. So you have one glucose molecule, then another glucose molecule. Okay, so this is the carbon number 1. So OH group attached to the carbon number 1, and it is the carbon number 4. So that two carbons, that is carbon number 1 of the first residue and carbon number 4 of the second residue, they are linked together through this oxygen. Okay, so this is the linkage form. It is between the OH group attached to the anomeric carbon and another hydroxyl group. Okay, another hydroxyl group of the another sugar. So that means it is a glycosidic linkage. That is what we discussed it when we discussed the formation of the O-methyl glucopyranose. Okay, so that we have already seen it. So it is the same bond that is linking one sugar to the another sugar. Okay, so two sugars, they are linked together by a glycosidic linkage, and since this molecule is formed by linking two monosaccharide units, they will be called as a disaccharide. Okay, now the linkage here, it is between carbon number 1 and carbon number 4, and if you see the configuration of the OH group attached to carbon number 1 of the first residue, then it is alpha. So that means it is alpha 1 to 4 glycosidic linkage. That is the name of the glycosidic linkage will be alpha 1 to 4. Means it is linking from carbon number 1 to carbon number 4. So it is carbon number 1 to 4. So alpha is the configuration. So alpha 1 to 4 glycosidic linkage is the name of this one. Okay. So here, if you see the anomeric carbon of the second residue, so here the OH group attached to the anomeric carbon with second residue is free. Okay, they are free. So that means this sugar will be reducing. So earlier, while discussing the reducing sugars, we have discussed that if the sugars contain a free anomeric carbon, then they are reducing. So here, this disaccharide, it contains the free anomeric carbon, so there will be a reducing sugar. So maltose will be a reducing sugar. Okay, so it is formed by an intermediate product of the action of the amylase on the starch. So generally how this maltose is formed is that when the starch is hydrolyzed by the action of the amylase, then it may produces the maltoses. Slide, we have seen that there are two glucose residues, and both these glucose residues are linked by a glycosidic linkage, which is formed between the carbon number 1 of the first residue and carbon number 4 of the second residue. So since the linkage is from carbon number 1 to carbon number 4, and the configuration of the group at the carbon number 1 of the first residue, it is alpha. So it is called as the alpha 1 to 4 glycosidic linkages. Okay, so this is just what is written here in the next slide. So both the glucose residues in the pyranose form. Okay, so that is in the maltose, and the configuration at the anomeric carbon atom in the glycosidic linkage is alpha. So maltose is therefore called that 4O alpha D-glucopyranosyl beta D-glucopyranose. This is the chemical name, but it's quite difficult to remember. You don't have to remember it. Simply say that it is the maltose. But if you remember this chemical name, then it will be easy for you to write the structure. The second glucose residue possesses a free anomeric carbon atom that is capable of existing in the alpha and the beta configuration. Okay, of which the beta form is the most predominant. So here, that if you see the second residue, then the OH group attached to the anomeric carbon. So this may be above the plane of the ring, or it is below the plane of the ring. Here, in this case, it is above the plane of the ring. So here, this configuration, it can be either in the alpha configuration, it can be in the beta configuration. So both the configuration it occur, but in most of the time this will occur in the beta configuration because the beta configuration is more stable. So that is what we discuss in the when we discuss the meta rotation. Okay, so of the 100, the 66% it occurs in the beta configuration because it is more stable. So here also in most of the maltose residues, the OH group attached to the anomeric carbon of the second residue will be in the predominantly it is in the beta configuration. Now, the glycosidic linkage is symbolized by alpha 1 to 4 linkage. Okay? The linkage involves the carbon atom 1 of the first residue and the carbon atom 4 of the second residue. So, since the linkage is from carbon number 1 to carbon number 4, that it is called as the 1 to 4 glycosidic linkage. Then the alpha comes because the configuration in the anomeric carbon of the first residue was alpha. So it is alpha 1 to 4 glycosidic linkage. Okay. Next is the lactose. Okay. So lactose is also a disaccharide found in the milk. So it is the milk sugar that is, and it contains 1 galactose and 1 glucose residue. So if you hydrolyze the lactose molecule, then what we will find is that you will get a galactose residue and a glucose residue. So here, let's see here, the first residue, if you see the configuration at the carbon number 4, okay, the OH group attached, it is above the plane of the ring. That means it is galactose molecule, okay. Then the linkage here, it is here that configuration at the anomeric carbon of the galactose, it is beta. So it will be from carbon number 1, then it is carbon number 4. And the configuration here it is beta, so this will be beta 1 to 4 glycosidic linkage. Okay, so here the two monosaccharide units are linked by beta 1 to 4 glycosidic linkages. Then similar to the maltose, the OH group attached to anomeric carbon of the second residue, that is the glucose residue, is free. So the lactose molecule is again a reducing sugar. Okay, similar to the maltose, it is also a reducing sugar. Okay, next disaccharide molecule, it is the sucrose. So sucrose, it is the cane sugar. Okay, so it is a disaccharide of the alpha D glucose and the beta D fructose. So here the mono glucose and the fructose. So here, the first residue is the glucose, then anomeric carbon, the configuration and anomeric carbon is alpha, okay, it is alpha. Then the second residue, it is the fructose, and here this is carbon number 1, carbon number 2, 3, 4, 5, and 6. That means the linkage is between carbon number 2 of the fructose. So here, the linkage form is carbon number 1 of the glucose residue and carbon number 2 of the fructose residue. Then configuration is alpha. So it is alpha 1 to 4 glycosidic linkages. Okay. Here, both the anomeric carbon, they are involved in the formation of the bond. Means none of the anomeric carbon is free in case of the sucrose. That is, anomeric carbon of the fructose, anomeric carbon of the glucose is involved in the formation of glycosidic linkage. So, since both the groups are involved in the formation of the glycosidic linkage, there is no free anomeric carbon. And since this molecule does not contain the free anomeric carbon, there will not be a reducing sugar. So, sucrose is not a reducing sugar. Now, this sucrose, it has a specific optical rotation of plus 65.5. So, if you measure its optical rotation, then it is dextrorotatory. Okay, it is dextrorotatory, and the degree of rotation is 66.5. So, on hydrolysis, it produces the alpha D glucose, and we know that for the alpha D glucose at equilibrium, they will have a specific rotation of plus 52.5. Okay, it is still just a rotatory with the 52.5 degrees. Then the other product form is a fructose. The fructose, it has a specific optical rotation of minus 92 degrees, means it is a levorotatory compound. Okay, so you have two molecules. One is having a dextrorotatory with a degree of 52.5. The other one is a levorotatory with a degree of 92 degrees, so with the rotation of the 92 degrees. So if you sum up these two, this becoming negative. Negative means it is levorotatory. So before hydrolysis, the sucrose was a dextrorotatory, but on hydrolysis, this will have a levorotatory effect, means it is inverted. So because of that, this is also called as an invert sugar. Okay. So on hydrolysis, the hydrolysis is accompanied by a net change in the optical rotation from the dextro to the levo. Okay, the hydrolysis is accompanied by a net charge in the optical rotation from dextro to the levo as the equimolar mixture of the glucose and the fructose is formed. Therefore, it is often called as an invert sugar because the rotation is inverted. On hydrolysis, the rotation is inverted, so it is called as the invert sugar. Okay, I think let's stop with this. That's better. Next time we'll start with the other disaccharides. Some more disaccharides is there. Some more this one, that oligosaccharides, we need to discuss it. So we'll discuss it in the next class. I think time is also almost over, and I have some guests, so we'll stop here.
Thank you, sir.
Thank you, sir.